Thank you all for joining us today. My name is Michael Driscoll. I am the CEO and co-founder of Metamarkets, and I'm here with Eric Cheddar, our lead architect. And today we're going to be talking about Druid. The title of this talk is Fast Ad-Hoc Queries on Big Data. And I'm going to speak for a few minutes to start, to provide some context for how it is that we came to build this data store. And first, I just want to give you a sense of what Metamarkets does, and then I will turn it over to Eric to talk a lot more about Druid and what it does. So Metamarkets, like many companies that you may have heard from at Strata, we are keenly interested in big data. And fundamentally, Metamarkets is not simply interested in reinventing business intelligence at scale on the cloud delivered via a web browser. We are interested in building a bridge from BI to data science. And we see this as critical because there's a new class of data out there in the world today, both in terms of its scale and its velocity, which requires a new kind of analytics tool and new components. We are huge believers and users of open source technologies. Our solution, this is our big data stack, is really inspired by a lot of the technology stacks that ourselves and our engineers developed internally at Silicon Valley companies. I've used this slide many times to illustrate how we sort of frame what a big data analytics stack looks like. It's sort of a four-layer cake. You've got ETL, often the hardest part. You've got persistence, a data store. This is where Druid comes in, as we'll talk about in a moment. Above that, you've got analytics. And finally, it's about visualizations and providing value to an end user, to a decision maker. And across the stack that Metamarkets has developed, we leverage open source tools. At the ETL layer, we use Hadoop and Kafka for real-time ingestion. At the data store level, we use Druid. At the analytics layer, we're big users of R and Scala. And finally, to power our visualization tool, we leverage Node.js as well as D3, a JavaScript to SVG library. And really, the big story that Metamarkets is sharing today is why we are open sourcing Druid. And fundamentally, at this data store level, we had no intention of building a database when we set out. In fact, when Eric first said to me, I'm thinking about rolling our own database, my response was, you've got to be out of your mind. I think no company goes about building a data store lightly. But we did so because we felt that Druid fills a gap. And I want to sort of throw some numbers out that really demonstrate what we were able to do with Druid that we weren't able to do with other existing technologies. Today on the Metamarkets platform, we process over 1 billion events a day across all of our customers. We process over 100,000 queries generated through human mouse clicks per day. And the average response time of every one of those queries is less than a second. That was the requirement that we issued for our technology, is that every single query, no matter how large, return in less than a second. That's the definition of something being interactive. And why does this matter? Why now? Well, I think this scale of data, as we all know, is becoming increasingly common. The volume and velocity of data is exploding. And I'm sure we've all seen many versions of this slide, but it's our contention that these high-volume, high-velocity transaction streams represent among and perhaps the most important class of data emerging in the world today. We've got this internet of sensors, of smart devices, and many of the companies that we work with are plugged into this more fully instrumented global digital nervous system. So I want to give a quick tour of the product. I'm not going to do a live demo. We're not that brave. But I encourage you to go to metamarkets.com if you want to check out the product. But really, this is to give you a sense of what the product does and where Druid plays an important role as a component in our stack among the other open source components. So really, the first thing that people discover when they come to Metamarkets is our discovery feed. And this is something that we think really differentiates us from others. We've been working for the last 15 months developing a set of anomaly algorithms that we push down to where the data lives to pull out the most interesting trends in our customers' data. And in this case, what I'm showing you is actually the global Wikipedia edit stream. Some of you probably have worked with this data before. It is a torrent of every single edit made to every single page by any Wikipedia editor around the globe. And using this real-time feed, which we are up to date within 6 seconds of when edits are made, we can pull things out, such as what's the most edited page in English in the last 24 hours. And not surprisingly, or in the last 2 days, Lance Armstrong has been a pretty popular, or should I say unpopular guy. And we can pick that up. That's something we sense. And we can very quickly drill down and start to understand why, or the how, or the what of this particular signal. We can break it down by what kind of languages are the folks who are editing Lance Armstrong's page speaking. Turns out English, of course, is first, but not surprisingly, French is second. We can take a look and see what some of the other relationships are in the Wikipedia stream. We can look at how articles compare to Wikipedia discussion pages. Naturally, articles are far more important. And finally, we can start to do things like pivot over all of the data, all of the edits that we've pulled in over the last 48 hours. We can look at who are some of the top editors by language. We sometimes call this internally at Metamarkets InfiniPivot, because the amount of data that's underneath, under the covers here, powering these interactive queries can be tremendously large, into the terabytes. And you can get instant feedback with every one of these queries. And of course, we support a large number of visualizations. This is just one showing a bar chart. But again, this is leveraging the D3 framework and some additional proprietary code that we've built on top of D3. So I guess with that, I want to turn it over to Eric Cheddar, who is the lead architect at Metamarkets, but most importantly for all of you today, he's the creator of the Druid data store that we are announcing the open sourcing of today. So with that, Eric, I'll turn it over and let you run.
Thank you, Mike. Hello, as Mike said, my name is Eric, and I am the originator of the Druid data store. We've got a number of other people that have helped make it what it is today, and it couldn't be where it is without them, but I'm here today to talk to you about Druid. What is Druid? And basically, this is our whiteboard diagram of Druid. What you have there in the center is the Druid, and then you have animals around the side with Winnie the Pooh and a honey pot down at the bottom. And this is a little doodle that I made that our marketing people really did not want me to put up here, but they're going to learn not to give me the slides before a presentation. But anyway, so what I'm actually going to talk to you about is RealTime Analytics. What does it mean? What were the requirements that we were going for? And Mike went into the product description, what it is we do, what it does, what we were trying to do, the experience we were trying to give to the users. And as we were coming up with this experience and trying to understand what we needed to build in order to provide that experience, we drilled it down into kind of these three things that we needed to do. We needed to have fast aggregations, or the potential to do fast aggregations over billions of high-dimensional events. We needed to have flexible drill downs at an arbitrary depth. We didn't want people to only be able to filter by up to 3 things, and then you can't filter anymore and you can't look deeper in your data, because as I'm sure everyone that's worked with data knows, anytime you set a limit like that, you're immediately going to hit it and want to expand it. All arbitrary limits that humans set, you hit them immediately and want to expand. It's the same with once you add more disk capacity, you're going to increase the amount of data that you collect and you're going to fill it. It's just one of those realities. And the other thing, as Mike mentioned, we want to do sub-second queries. We wanted to give people a fast experience that really allows them to interact with the dashboard and explore the data rather than thinking, okay, I want to look at this, so I need to build my query like this and do this, and now I'm going to run it, and then go get some coffee and come back, and oh, I did that slightly wrong, let me adjust it a bit and do it again. We wanted people to kind of see the data, look at it, be like, oh, these are the top countries, let me go into that, and really interact. And so these were the requirements that we set out with. And one of these also, the fast aggregations also includes this idea of real-time and actual real-time data ingestion. And so real-time is this term that's talked about widely, and in some cases it means fast queries. It means that when you do your query, you get the result back and you can see stuff quickly. Other people use it to refer to, I just got the data and now it can be reflected in my query, but the query might take a minute to actually run, and so there's the latency there. And then there's kind of the marriage of the two, getting fast queries on top of data as soon as it's immediately available. And that the real time that we believe in and the real time that we've set out and that we've implemented is the marriage of both. It's you get the data and it's immediately available to be queried, and you have fast queries on top of it so that you can actually see it without waiting a long time. And those are the requirements that we set out with to build. And as we looked at it, we said initially this problem, it's a traditional data warehousing, business intelligence problem. We're not trying to reinvent the wheel. What we want to do is give users a good experience and try and help them have a good experience. And so the first thing we did, we used a relational database because that's what people use in this field. A lot of people have been working in the field for a long time, and they use some sort of relational database. Generally, they have a star schema. They set up a bunch of aggregate tables. They put some query caching in front of it, and then they're running and they're off to the races. And that's what we did. We set that up. And queries that were cached were definitely fast. And queries that ran against aggregate tables, depending on the size of the aggregate table, they were fast to acceptable. It ran within the time bounds that we cared about. But as soon as we got a query that wasn't cached and that we couldn't use an aggregate table for, we had to fall back to the base fact table, and scanning that ended up being too slow for what we were going for. And what does too slow mean? From some benchmarks we ran on a relational database system, we did a pretty naive, just count the number of rows in this table, and we benchmarked it at about 5.5 million rows per second per core. For the data sets that we deal with, if we summarize down to, let's say, 60 million rows for 1 day's worth of data, that means on a 16-core machine, we're looking at a 5-second query. Now, on our dashboard, we generally show a 1-week view. And so that means for our dashboard, we're looking at 7 days of this. So we're looking at about 420 million rows that need to be scanned in order to produce the results for one query on that dashboard. However, on our dashboard, we're not just doing one query. We do one query for a time series, and then we also do dimensional facets. And so each dimensional facet ends up being its own query. We have some deltas, and we do some other things in there. And on average, we have about 15 to 20 queries per page load. And so when you take that and you say, okay, one query takes 5 seconds, 20 queries, that's a long time. That's not the experience that you want to have or that we wanted to give to our customers. And so then there's the question, well, you can distribute out. At that point in time, looking at things, you have to basically go and talk to a vendor who is going to take a lot of money. And we were a startup without a lot of money, and trying stuff out, trying to find something that's cost-effective for us that will allow us to do things. And so we said, the relational database isn't going to work for us right now. So what did we try next? We moved on to Nosql. NoSQL, everyone loves NoSQL. It's awesome. You get all the benefits of kind of auto-scaling and a bunch of other things. At the end of the day, they're basically key value stores each of them does something clever that makes them work well in one use case or another, like improve range scans or other things like that. But at the end of the day, a lot of them are primarily key value stores, and we took a NoSQL key value store and basically said, we're going to use this. We're going to try it. How did we use it? We pre-aggregated the dimensional combinations. We're trying to give you the ability to filter down into the values, and so if we pre-aggregate those filters, then we can load them up with just a simple query, get the data, show it to you. It'll all work wonderfully and be great, and the NoSQL is going to scale for us. So even though we're increasing the amount of data we're going to store, it'll scale and we'll be fine, was the thought. And so we did that. The results were that queries were definitely fast. The range scan, it's basically a range scan on a primary key. There's a lot of NoSQL stores that can do that very well if you set up your key structure properly, and that was wonderful. They were very fast. However, it was inflexible. If it's not aggregated, it's not available. You have to pre-aggregate everything that you ever want to see. It's also doing things like top lists in this sort of environment also becomes difficult. It becomes difficult to figure out what are the top values of this one dimension. You essentially, and what we did was have to pre-aggregate the actual top list as well, which adds to another degree of inflexibility. It's also not generally continuously updated. If you set up a real-time system in front of a NoSQL store, given that it's a key value store, basically the handoff point to make something available in a query is when it enters the NoSQL store. And so what you do is you have a system that's basically aggregating as it goes, and then it dumps into the key value store. It dumps into your NoSQL store, and then you can query it and see it. And so whatever your latency is on aggregating before you put it in, so if it's a minute granularity, you're introducing a minute worth of latency before you put it in the system and make it available for queries. And we wanted to be able to show 30 seconds of the minute and give you partial data for that minute. And so that was something that we weren't too happy about either. But the real big thing was that the processing scaled exponentially. Pre-aggregating all of the dimensional combinations, it just did not work. And when I say it did not work, what do I mean? Well, it did not work, basically. We tried doing something by limiting the dimensional depth. So say you have 10 dimensions. You don't need to filter on all 10 dimensions. Maybe you only need to filter on 5 dimensions, 4 dimensions, something like that. You don't need all of that. No one's actually going to look that deep. And so we said, sure, we'll limit it to 5 deep. We'll only go 5 deep. But the problem is, even if you limit that, adding new dimensions is still an exponential growth in the number of keys and the number of things that you have to pre-compute. And to kind of exemplify this, as an example, we took a 500,000 row data set. This was kind of the straw that broke the camel's back for us. But we took a 5,000 row data set, and with 11 dimensions, limited to a depth of 5, and we computed all the combinations. It took 4.5 hours on a 15-node Hadoop cluster, produced over 1 billion keys, and we stored it. It was fine. It was queryable. At this point in time, we weren't doing real-time stuff yet. We were only loading in batch every night. And so we were like, hey, we can run this every night. That's fine. It's a little bit of latency, but yeah. Then the customer came back and said, I really want to see these 3 other dimensions. So we said, OK, we'll add them. And we added them. We ran it. Ran really slowly, so we grew the cluster. And it turns out that it took 9 hours on a 25-node cluster to add those 3 dimensions. And we looked at that scale trajectory, and we were like, there's something not right here. This is not going to work for us as we keep going. We're not going to be able to get to a 30-dimension data set with this sort of scaling. And so we decided NoSQL wasn't going to work for us. And so then we were back at the drawing board, basically trying to figure out what do we do? How do we solve this problem? And the thing to do when you're back at the drawing board is say, what have we learned so far? And what we learned is that the relational database model, the way that you store the data is actually the smallest representation of the data. It takes advantage of sparseness in your dimensions. For dimensional combinations that don't exist, you don't store the data. And so that 500,000 row data set is a 500,000 row data set. That's all it is, and that's all you're ever storing. And that's actually optimal. The only problem was that the relational scans, when things weren't pre-aggregated, was slow. The NoSQL problem, at its heart, was that the way we were doing things was computationally intractable. You can't pre-compute all of those dimensions and you can't handle that exponential increase if you want to allow for arbitrary drill down in your data. And when we looked at these two problems, it looked like the relational database problem was a lot easier to try to tackle and fix. And that is what caused us to create Druid. Basically, I sat down and said, okay, I've got this data set. I think I know what a relational database would do with it. Let me go off, and my language of choice is Java. And so I went off in Java and said, okay, I'm going to take this row of the number of impressions, and I'm going to add them together. How long does it take me to add 5 million impressions as an int array in Java? And it turns out it's really fast to add those together. It's very, very fast. And I was like, okay, that's the speed that we need to be able to run at. And then I spoke with Mike and was like, hey, kind of seems like going with our own thing might be interesting. We were looking at a couple of different search-based systems as well, like SenseiDB out of LinkedIn and a couple of things like that. But I won't get into too much of that. I'm going to go into how Druid actually works, because at the end of the day, we did decide to go and implement our own thing, and I'm going to talk about that. And basically, this is the feature set of Druid. There's kind of 5 things. These are buzzwords that you probably hear all over the place these days, but we're going to say them too. It's a distributed column-oriented store. It supports real-time ingestion. We do fast data scans, fast filtering, and it's operationally simple to manage. The way that we operate, we're primarily on AWS. We don't have a heavy ops team. The developers are the ones who are keeping things up and running, and so if something is difficult to run operationally, the developers feel that pain, and we kind of don't like it. We like to be lazy and not think, and so we tend to implement things that make it easier for us to do our jobs. And out of that, I think we've gotten a fairly operationally simple thing to run. Going through the features one by one, we have a distributed column store. What does that mean? Just at a high level, what we do, we take the data, we chunk it up into individual segments, and then we have an MVCC swapping protocol, a multi-version concurrency control swapping protocol. Basically, you can take new data for a segment and atomically swap a segment for an old segment. This is similar to kind of how Voldemort does swapping of its read-only segments and other things like that. We also take the data, and it's generally row-based as it comes in. We convert it into a columnar format. We have a coordinator node that basically understands I have n number of machines in my cluster. I have x number of segments. And I want these segments to be replicated some amount of time. And so it says, okay, you 3 guys, you load this segment. You 3 guys, you load that segment. And it just kind of keeps watch over things and makes sure that all of the data is somewhere where it should be. And the replication factor, like the way that this is structured, it allows the coordinator to basically, it can tell any number of compute nodes to load up the same segment. And so you can get a replication factor on an individual segment equivalent to the number of compute nodes that you have, which helps to deter hotspots and helps to basically handle some issues that you often run into in distributed systems, especially when you're trying to run a service or a product on top of it. And then there's the real-time ingestion. How does real-time ingestion work? This one is, everything's probably better described with a picture, but this one is definitely better described with a picture, and so we have pictures. And so right now, we have our historical node cluster up there. That's what I just kind of described. We have all these nodes out there, and there's this coordinator that tells different nodes to have certain data on them, and and do things. And this exposes a query API, or each of those nodes exposes a query API. Then we have some broker nodes. And these brokers, they understand the data topology. They know what data exists on what node. And when they get a query, they can basically take that and say, OK, I need to look at these chunks of data. So I need to route this request to these different servers. It rewrites the query for each of those servers, sends it out, gets the results, merges them together, and spits it out. It's a traditional scatter-gather pattern, very heavily used in search-based systems, and it's the same basic architecture, hierarchical querying, and all that good stuff. So that's kind of how the main cluster works, how the historical nodes work. And now, we haven't described real-time yet, and that's why we have the space up in the top left. What we did for real-time is we have another set of nodes that basically we have the blue dots up in the, oh, it's not the top left, the top right. Oh, no, it is your top left. Never mind. We have the blue dots up in the top left that represents the fire hose. That's the stream of data coming in. And basically, we have these real-time nodes, and each of the nodes connects up to the stream and processes the events as they come in. And in processing the events, they load it up into an in-memory store, and they just keep it in there. And the thing about this is that the real-time nodes actually expose the exact same query API as the historical nodes. And so the historical nodes, they publish, I have this data for this time segment, and so that the broker can query it. The real-time nodes use the exact same mechanism. They say, I have data for this hour, and that hour happens to include right now. And so the broker, all it does is when it gets a query that happens to include right now, it routes that part of the request over to the real-time node. It routes the historical part of the request over to the historical nodes, gets the results back, merges them together, and spits them out. And so you have this one cluster that combines both real-time nodes and historical nodes, and real-time and historical query processing in the same query interface so that your client doesn't have to think about it. They don't have to know whether or not they're talking to something that's real-time or not real-time. And then one of the other problems with doing real-time, especially storage of real-time, is the memory concerns. When you're doing this historical, a lot of times if you're taking the real-time data and you're storing it on that same node, you start to have this mismatch of memory concerns where your historical data processing is generally crunching over the same data over and over, but you have more data on disk than you do in RAM, and you want to handle your hot and cold segments, where your real-time nodes have, they basically have a stream that they always have to be processing. They have to process that as fast as possible, or you want them to process it as fast as possible. And they need to keep an in-memory representation updated so that it can be queried. And when you merge these two concerns together, it becomes very difficult to keep your systems up and running because you can get some queries that will topple over your real-time nodes, your stream can end up toppling over your historical nodes, and you can run into issues. And so what we do instead is we have the real-time nodes basically roll data off into the historical nodes. And so on some time bound, the real-time node, say for example, it aggregates up data for an hour. And so it builds up an hourly segment and checkpoints it to disk at certain intervals. Then at the end of the hour, it takes everything it's checkpointed, merges it together into one segment, and then throws that over the wall to the historical nodes. As soon as the historical node loads it, the real-time node doesn't have to worry about that data. It can delete it off disk. It can remove everything it has in memory and just keep processing on the current stream. And so the real-time node only ever has to worry about the most recent window of time of data that it has to process. And that window is configurable for the number of events that are coming in. And so this is, I apparently have 9 minutes left, so I'm going to have to move through this a little quicker. And that's how we handle real-time data at this point. Kind of how do we do fast data scans? We do it the same way everyone says that they do it these days. I don't know what just happened. Okay. We use column orientation, which means you only load and scan the data that you care about, and we use compression, decreases the size of your data, and all of that stuff. Fast filtering. How do we do filtering? All of the segments actually maintain indexes of the data in there. We maintain bitmap indexes for all of the values of the dimensions. We compress the bitmap indexes to decrease the size, but we use this concise compression, it's a variant of word-aligned hybrid, for those of you who know what that is. You can Google it. There's a paper about it and everything. But we've implemented this, and it allows you to do binary operations and or and not on the compressed form of the bitmap. And so with these bitmap indexes, basically what we can do is when a query comes in with a filter, we can use the bitmap indexes to figure out which rows match that filter and only load those rows and only process those rows. So we never have to process a row that doesn't match what we're doing. Every row we process has useful information. We don't throw it away, and that allows us to filter, and we can figure that out before ever looking at the data. And it's operationally simple. It's fault tolerant, primarily due to the replication. We do rolling deployments and restarts. Our production cluster, we've had no downtime due to deployments for the past year, I believe, and we generally, sometimes we'll deploy multiple times a week, sometimes we'll deploy after a 3-week break, but we basically do rolling deployments and just keep things running, and that's really nice. We grow the cluster by starting new processes. We shrink the cluster by killing processes. It's pretty easy, and you don't have to do much more. It figures out what it should do with that. Druid in action, what can you do with it? You want to get data out of it. There's a query interface. What you see on the slide right now is SQL. The query interface is not SQL. Some of you might be happy, some of you might be sad. It is JSON instead, but it basically represents the same thing. The primary query that we provide is a group by query. You can say group by, this is on the Twitter Spritzer data source. It's going to process the current day, give you data at an hourly granularity, give you the group by of the language and hashtag dimensions, so all of the hashtags tweeted out on the Spritzer for broken down by language, and is going to aggregate the number of tweets and tell you the number of tweets out there, and filter by the United States. So basically, this query would give you all of the tweets broken down by hashtag and language on October 1st for every hour from the United States, is basically how that's built. The features that we have for the querying, like I said, it's a group by query. We do time series rollups and give you kind of granularity functions to make it easier. We allow for arbitrary Boolean filters. There's your basic aggregation functions. It's a pluggable aggregation architecture, so you can add more as well, but sum, min, max, average, and other stuff. You can do dimensional search, explore what the actual dimension values are to understand that. Then there's a comparison of some of the other things that exist out there. How does Druid compare? How should you think of it? And I think the three main players, and I guess Cloudera just announced Impala today, and so they're not on here because I don't know anything about them, but Google Dremel, Google PowerDrill, and Hadoop Avro Hive Yarn combination. And the closest analog to Druid, I'd say, is Google PowerDrill, which was announced at VLDB back a month ago. It's basically an all-in-memory system that does some smart things with compression and sorting in order to decrease the data size. The primary difference between Dremel and Druid is that Dremel doesn't really have an indexing structure. It does pruning of the query and basically can do high-level, this chunk of data only has this stuff, so I don't need to look at it, but whereas Druid will do that, but it will also do the inside and use the bitmap indexes to figure out exactly which rows match or don't match. And then there's the Hadoop Avro Hive Yarn, which I believe is closer to kind of the Google Tenzig use case, which is another paper they put out about a year ago. And the use cases here are generally back office use cases, I believe. I don't know. Well, anyway. I might be wrong, but I believe they're generally back office. And one of the other things is the Hadoop Avro Hive Yarn. It doesn't yet do real-time data ingestion in the same way that we do, and the real-time is really kind of important to us. Some benchmarks. We've achieved 33 million rows per second per core scan speeds. with our cluster, and so we're pretty happy about that. Our real-time ingestion rate is about 10,000 records per second per node. And before open sourcing, we approached a couple of development partners, and one of them is working the system into their production. Right now, they're aggregating 2 billion events per day in real time, and we're pretty proud of that and happy. We've got, as a cluster example, the largest cluster I know of is 100 nodes. It's 6 terabytes of memory, 400 terabytes of disk. On a 6 terabyte data set, we were able to run a query that ran in 1.4 seconds using all of the horsepower of 100 nodes. But that's pretty fast and something else that I'm pretty excited about. As I said, Druid is now open. We opened it up last night. I was up till 5 a.m. doing the last changes of the code and making sure everything was there and throwing license files on top of stuff. You can learn more about it at metamarkets.com/druid. You can check out the code at github.com/metamx/druid. I'm very... also, you can contact me at cheddar@metamarkets.com. If you're wondering, that's how you pronounce my last name. And my Twitter handle is Zdruid. You can tweet to that. I'll try to be responsive. Hopefully, this is helpful to you guys. Hopefully, it can do something for your organization. I know I've really enjoyed building it. The guys back at the office have really enjoyed building it. And if you have any questions, problems, want to work on it, want to contribute, all of that, I'd love to hear from you. Yeah.